Hello everybody, and welcome to an extra lecture segment for 6838. Today we're going to cover a particular algorithm for a task called angular synchronization that I think links nicely into our discussion of consistent correspondence. Basically, this is another algorithm that's sort of similar to the semi-definite programming technique that we derived in lecture, but in this case, it applies to a slightly different input-output pair, and I thought was kind of a good way to reinforce some of the ideas that we covered during our main lecture. So in case you're curious, the paper that we'll be going from is by Amit Singer, S-I-N-G-E-R. It's on angular synchronization. I think the whole title is like angular synchronization with eigenvectors and semi-definite programming. And this was in the applied computational harmonic analysis in around 2011. There are actually a few different versions of this paper floating around with different years attached to them, but I think 2011 is the official one. So I'm going to give you a bit of motivation for our problem, and then we're going to derive the actual algorithm that is proposed in this paper for solving the angular synchronization problem. And we'll see that it has a lot in common with the consistent mapping through semi-definite programming technique that we just covered in our previous lecture. This algorithm also comes with really nice statistical guarantees, which are a bit outside of the scope of 6838, but once you get the idea of how the algorithm is derived, I encourage you to give the paper a read, because I think there's some really interesting ideas hiding in there. So the basic setup here is that as input, we're sort of given a bunch of different copies of the same signal. But, of course, our problem isn't that easy. We have two different things that get in the way. Each of them is quite noisy, and they're rotated. Now, specifically in the angular synchronization problem, this is going to be a one-dimensional signal. Okay, so let me see if I can make it a little bit more concrete for all of you guys. So let's say that we all are wearing smartwatches that are like tracking our 24-hour cycle. So maybe we look at, I don't know, your heart rate, blood pressure, whatever, as some function of time. And what I get back is some signal which is tracking some biological thing. So maybe here, rather than using a 24-hour cycle, we're going to use a 2-pi cycle just for convenience. But maybe, every morning I wake up, I get really excited because I woke up, so my activity kind of increases. And then I eat breakfast, so I'm excited again, and then the rest of my day is pretty boring. So that's the signal that comes out of a 24-hour cycle in my smartwatch. And now I go out and I do a study, and I get a bunch of different signals from different people, and they all have a very similar structure, but the problem is that we all go to sleep and wake up at slightly different times. Maybe somebody's in a different time zone, and their signal gets shifted to the middle of the day. And remember that, of course, these, when we have shifts here, they're in 24-hour cycles. So it could even be that like one of these bumps is here, and the other one is over here, right? They're all cyclically permuted from one another. So one way that I can understand this is that somehow, if I take a look at like where this trough lies here, and I look at where it lies in the second graph, there's some distance between the two, which is the amount of shift that happened. So essentially what I can say is that, what we're given as input here is going to be some estimate of the shift between each of these signals, because our goal at the end of the day is to synchronize them all. But the problem is that they're all inconsistent. Now, let me see if I can add a little bit more detail to that. So in reality, our smartwatches are, quite noisy sensors. So we don't get these nice functions as a function of the 24-hour cycle. Instead, we get something extremely noisy, okay? And we only know them up to a constant shift. Okay, so between every single pair of these, right? So maybe between like subject A here and subject B, subject C, I can kind of come up with some estimate of, you know, the best way to align A to B, the best way to align A to C by cyclically permuting, but I expect that that estimate is going to be quite noisy. Right? So at the end of the day, I want to have just one 24-hour cycle that averages out everybody's data, but the problem is that they're all shifted from one another. So in the angular synchronization problem, my goal here is to find an angle so that, like, you know, I can take this guy, shift it to the left by this amount, right? So in this case, I guess maybe I'd call this delta AB or BA, whatever. And after I shift it, then it makes sense to average all of these signals together to get rid of the noise. Okay, so let me see if I can add a little bit more detail. Essentially, between every pair, I, J here, where like I and J index into my different smartwatches, what I get is an estimate delta ij, which is sort of given the best cyclic shift of signal I onto J. Incidentally, I'm probably going to screw up the sign of ij versus ji. In fact, I think I already just did that. So you guys are going to have to bear with me, as always, in this class. But if you made it this far, you're probably used to it by now. Okay? So in other words, what we want now, here's the problem, is that like I know how to shift signal B onto signal A. I know how to shift signal C onto signal A. I can also shift signal B onto signal C, but there's no reason why these things are all consistent with one another. So at the end of the day, you know, if I think I want the delta ij here is roughly equal to theta I minus theta j. So the idea here is that between every pair of signals, I can, just by like enumerating every possible rotation, I can find the best rotation that shifts one of these guys onto the other. But they're not cyclically consistent, so I'm going to make them cyclically consistent by assigning a theta to each of these that puts them in kind of a common reference frame. So like maybe shifts this guy to the left to align with signal A, maybe shifts this one to the right a little bit, you know, to move this bump over to the other side, and so on. So, right, if we want to distill our problem a little bit, essentially, one way to understand it is that we're given a bunch of delta ij's, which are roughly equal to the difference theta I minus theta j. And what we want to compute, what we want to find is spelled with a D, fun fact. Thing is a set of theta i's that are consistent with these deltas here. Now here's one problem. We only ever observe the differences between the theta i's. And that actually makes sense. So for example, what would happen if I added like 32 degrees to every theta here? Well, it turns out the answer is nothing, right? And that's all to say that, like, you know, who says when that 24-hour cycle starts, right? I could shift everybody to align to signal A, you know, so I move B to the left and C to the right. Or I could have shifted all of my signals to align to signal B, right, by moving A to the right and C, well, either to the left or the right, it's not super clear. And that would actually be an equally good answer to this angular synchronization problem, which is to say that sadly, our solutions are not unique, right? If I add a constant angle to all of my thetas, I actually will get an equally good solution to the angular synchronization problem, and that somehow feels like it's getting in the way of properties like convexity. Okay, so that's our basic setup. By the way, the word angular here maybe is a little bit weird given the intuition that I set up, but notice that, you know, essentially we're viewing this as a 24-hour cycle, so I could have understood, for example, signal A here as sitting on a clock face, So maybe, here is noon. So I have some function that looks kind of like that. And then signal B, which is somehow shifted a little bit forward, is another function. Here I'm viewing it as kind of a height over the unit circle, which lives over here somewhere. Right? And so my goal is to figure out the fact that, here this peak is at some angle, which I could think of as maybe theta A in this case. And here the same peak is at a different angle, theta B. And I'd like to know those different theta, so that way I can just kind of rotate all these signals into one common frame and average them. Notice that this is actually like somehow the simplest version of the consistent mapping problem. Do you guys see that? Let's make sure that we understand that basic intuition. So remember, in our consistent mapping lecture, essentially as input to many of our algorithms, what we were given was like a map from domain A into domain B, and a map from domain B into domain C, and a map from A into C, and so on. So here our maps are just given by rotations, right? So all we can do is take our data and just kind of rotate it like that. And our goal here is to find a consistent set of rotations that puts everything to one frame. So basically, it's just like the permutation synchronization problem we talked about in class. But instead of having permutations, now we have rotations, because we're going to say that that's like a simpler group that's acting on our data. So even if you didn't follow every detail of our setup here, hopefully you get the basic point, which is that we're given a bunch of relative rotations, delta ij, and our goal is to extract the thetas from this, even if the deltas are a little bit noisy. Okay, so I'm going to put a box around this formula here, if my paint pen will allow me to. And now we're going to erase to clear out a little bit of space. And again, to repeat, the reason why this problem is so difficult, well, one reason is the deltas here tend to be extremely noisy, right? Because aligning any two signals with each other can be really, really difficult, especially in the sort of low signal to noise ratio, like if these functions are super wiggly. And moreover, it's difficult because if we add a constant to any of our thetas here, we actually didn't change the solution. Okay, so let me clear out a little bit, and then we'll keep going. Okay, so now let's start tackling some of what makes this problem difficult. Now, there's a number of different ambiguities that go on in this angular synchronization problem, which are sort of simpler versions of some of the ones that show up in consistent mapping and other things that we've considered. So one of them is actually hiding in this expression I wrote here, right? Delta ij is equal to theta I minus theta j. But of course, we know that there's one issue with angles, which is that we only know angles up to a additive multiple of 2 pi, right? So we might call this the 2 pi ambiguity, which is to say that we don't really know delta ij as an approximation of theta I minus theta j. The best that we can hope for is that we know delta ij is approximately theta I minus theta j up to, I guess if we're going to be grown-ups, maybe we say modulo 2 pi, right? And this has nothing to do with our estimation procedure. It just has everything to do with the fact that angles are annoying to work with, right? So never mind the additive ambiguity in our problem, that if we shift all the thetas, the deltas do equally well. But in addition to that, we only know the deltas up to an additive integer multiple of 2 pi. So how can we deal with that? Well, one typical thing to notice is that, of course, cosine and sine, when we evaluate them, those things don't change if I add a multiple of 2 pi. Or because this is a graduate level course, rather than working with cosine and sine, a very typical thing for us to do is instead to work with complex numbers. So let's do that. In particular, we're going to make a few different definitions. So rather than writing delta ij is approximately theta I minus theta j up to an additive multiple of 2 pi, that's a big sentence. Instead, we can write a slightly different thing, which is to take both sides of this expression and put them inside of a complex exponential. In fact, just for fun, by the way, I'm going to add theta j to both sides. That's going to be useful for convenience. In fact, maybe I'll write it. So here's theta j plus delta ij approximately theta I. Hopefully we're okay with that particular thing. So in particular, again, all of this is mod 2 pi. So to get rid of that 2 pi factor, let's just put all of this in an exponential. So in particular, we can write the following, which is e to the I theta j times e to the I delta. I've learned in teaching online that I can say one thing and write another quite easily, for some reason. Okay. E to the I delta ij is approximately e to the I theta I. By the way, there's like a slight kind of notational overload, right? These i's are the complex, like square root of -1, and then there's the I next to theta, which is the index. This is also in the original research paper, and I think it's pretty clear when I is the square root of -1 and when it's an index. But just for completeness, I'll mention it. Okay, but notice that I no longer need this mod 2 pi anymore because the complex exponential actually takes care of that. So let's make a few definitions. In particular, what we're going to do is to define a value zi, which is e to the I theta I. I'm realizing that saying that out loud is kind of hard to parse, but hopefully it makes sense. I'm going to define capital H ij is equal to e to the I delta ij. Well, then by this expression here, now we can simplify things a little bit, which is nice. In particular, we have e to the I theta j, so we have a zj is equal to, did I already manage to make this a little bit wrong? Theta j. Oh, no, yeah, this is fine. Okay, so zj times hij is approximately equal to zi. Okay? So, right. Let me see here. E to the I delta ij. Oops, let me pause for a moment. Ooh. Okay, I paused the video for a second and convinced myself that I didn't make a mistake in my notes. Okay, right, so this expression is indeed okay. And now if we multiply both sides by zi conjugate, now on the right-hand side, notice that zi times zi conjugate, that's just the norm squared of zi, which is 1 by definition. So what we get is that, let's write it like this, zi conjugate hij zj is approximately equal to 1. So this is just a really slick way of writing our original problem here. But now, essentially what we've done is gotten rid of that shift by a constant integer multiple of 2 pi issue that we had before. So now we have this sort of interesting incarnation of our synchronization problem, right? So the HIJs are kind of like an inconsistent set of maps, where HIJ is basically this encoding of delta ij, like some inconsistent set of rotations. And now the idea is that HIJ is kind of like, if I want to cancel HIJ out, what can I do? I can rotate by theta j minus theta I. And that when we compose all this together, so like from I to j back to I should get the identity, right? That's what's hiding in this fancy complex valued expression here. Okay, whew, made myself nervous, thought I screwed up I and j already in my notes. So the reality is that if our delta ij's here are inconsistent, then this really is an approximation. So again, actually, let's make sure that we remember what our problem is, right? So our inputs are the deltas, our outputs are the thetas, right? So now our optimization takes a slightly different form, which is given the hij values, what we want is to maybe find a bunch of zi's. And notice that, okay, so for one, the zi's are complex value. And because they're like cosine and sine of an angle, they satisfy that they are norm 1 in the complex numbers. So if we want to optimize, then, well, we'd like this expression to be approximately true, but it can't be exactly true. So maybe we write down a pretty reasonable least squares problem, which is to find the z's minimizing the following, which is the sum over all ij pairs of, well, the left-hand side minus the right-hand side norm squared, right? So this is zi bar hij zj minus 1 absolute value squared. And just, as a sanity check, if you kind of follow our derivation backward here, you'll notice that this expression here is nothing more than e to the I, let's see here. So I guess this would be like theta j minus theta I plus delta ij. And notice that theta j plus delta ij minus theta I should be roughly 0, and e to the 0 should be approximately equal to 1. So we've actually managed to write an expression here that makes sense. Okay, so let's simplify this least squares expression a little bit. Oh, by the way, before continuing, notice this sort of expression here, right, that this thing should equal 1. This is just cycle consistency, right? This is saying that, if I map from I to j and back, I get the identity. So it's sort of like a 2-cycle in some sense. Okay, so in any event, let's simplify our expression a little bit. So what are we going to do? Well, we see a norm squared, so we should probably expand the square, as we like to do in this course. Now, we have to be a bit careful because we have complex numbers here. So remember that the norm of a complex number squared, or the absolute value of a complex number squared, whatever, is really the same as multiplying it by its conjugate, right? So we're going to get that this is zi conjugate hij zj minus 1 times the conjugate of this expression, which is zi hij zj, where these two guys are conjugated. And of course, the conjugate of 1 is 1. Okay. So now we have a quadratic expression. Let's multiply it out. So what are we going to get? Well, remember that complex valued multiplication is commutative. This is where angular synchronization and SO3 synchronization fall apart a little bit. But anyway, let's multiply out all of these things. So we're going to get like zi bar zi, hij bar, and then zj bar. Okay, so that's this one. And then we're going to have minus, well, it'll be zi bar hij zj minus zi hij bar zj bar. So if you work that out, that's actually just 2 times the real part of this expression here. So this is really minus 2 times the real part of, let's maybe write it as zi bar hij times zj. Okay, and then finally we have 1, plus 1 times 1. Okay. Whew. So here's the thing. Remember that by definition, the z's are unit complex numbers, right? So zi times zi bar, that's equal to 1. Similarly, hij times hij bar, well, that's another unit complex number, so I get another 1, and then a third one. See, a sneaky thing happened, which is that this is really just a complicated expression for 1. So in other words, really the only terms that matter here are the cross terms. So we can write this as a constant, right, which is going to be like, what, n squared. Really, we get 2 of those because there's a 1 here and a 1 here, but whatever. Minus 2 times the sum over ij, the real part of zi bar hij zj. Okay? Right. So this, what is this really telling us? This is telling us that when we optimize, if we want to solve our least squares problem here, like we want to find the z's that minimize this thing, well, notice there's a minus sign here. So our angular synchronization problem is the same as maximizing this expression. Okay? So at the end of the day, what is our goal here? We're given a bunch of unit complex values hij, and we'd like to find a bunch of unit complex values zi that maximize this expression, which thankfully we can see is real valued, so it makes sense to use it as a objective function. And that's really just a fancy encoding of our original problem all the way up here on the right. Okay, so let's actually write down this problem in more detail. I'm going to actually erase the entire board here, so take note. And just remember the z, well, in fact, maybe I can even write it here just so we don't forget. So let's define zi is equal to e to the I theta I, and that hij is equal to, these are by definition, e to the I delta ij. Okay? So I'll just copy these 2 expressions so that we have them handy. But the main point here is that if we know the z's, we know the thetas. If we know the thetas, we know the z's, and similarly here. Okay, so we'll just put that in our little pile of useful things. And so our input is the h's, which are like inconsistent maps, and our output is going to be the z's. And we're going to get them by maximizing this expression here. Okay, so let's erase a little bit and write our optimization. Okay, so given the expression that we just derived, essentially if we want to solve the least squares problem that gives us a synchronized set of angles, I think here's the kind of reasonable formulation that we can write. So again, we want to maximize now because there is a minus in front of that real term. And our variables are going to be the zi's. And if you recall, our expression looked like the following, which is a sum over ij, the real part of zi bar hij zj. Now, of course, rather than only having any possible z variable, that's actually not good enough, right? We need a constraint, which is that the zi's are all unit length in the complex numbers, right? In other words, they look like e to the I theta. Otherwise, if z isn't unit length, then we can't recover a theta using this expression here. So this is our optimization problem for angular synchronization, which I think is really tidy. This is a really nice way to phrase this problem. And essentially all it's doing is trying to find the least squares fit of the deltas after accounting for that 2 pi shift. But there's only one problem, which is as an optimization problem, this is a really difficult thing to solve. In particular, notice that there's a bunch of constraints, right? That essentially every single variable zi here has to be a unit length complex number. So in other words, really we have an optimization variable over a product of a bunch of different circles, which makes sense because we have a bunch of different thetas, which are angles, which is what this problem is really encoding. So this is a wildly non-convex problem, the way that I've written it, right? There's one angle basically for every single I. Now, what's proposed in this really nice research paper from Amit Singer, which led to a lot of different extensions to different problems, so I think it's worth covering, are different relaxations of this really difficult problem. The basic idea here, hopefully the word relaxation makes some sense, but the basic idea of a relaxation is that I'm going to remove constraint from an optimization problem to make it easier to solve, and hope that removing those constraints doesn't totally destroy the output. Right, so after you relax, you need to actually prove a theorem that says that your relaxation often will give you a useful answer anyway. And so in this Singer 2011 paper, they actually proposed two different relaxations of this problem. One of which is sort of easier to solve but weaker. So relaxations. And those are, one, using an eigenvalue problem, and two, using a semi-definite program. Okay? Now, at this point in this course, I think you've actually tried out a semi-definite program on your homework, which is convenient because it makes my life a little bit easier in our lecture today. So I thought we'd really quickly derive both of these just so you have some flavor of the type of computation you can do here. So let's do case number one, which is to come up with an eigenvalue relaxation. So here's the basic idea of the eigenvalue relaxation, which is that if Zi is a unit complex number for all I, well, if I have n variables, then what do I know? I know that the sum from I equals 1 to n of Zi squared, well, what is this thing? Well, it's just 1 plus 1 plus 1 plus 1 plus 1, so you get n. Okay? So at the end of the day, here is a relaxation, which is a pretty serious relaxation as they go. We're going to remove a lot of constraints from this problem. In particular, rather than constraining every single Zi to be a unit complex number, I'm just instead going to make one constraint of this form here. So here is one way to relax our problem, maybe call it star, which is to solve the following, which is the max over Zi of the sum over ij, the real part, Zi conjugate hij zj. But now we're just going to have one quadratic constraint, which is the sum of I equals 1 to n of Zi squared is equal to n. So this is a very relaxed version of that problem marked star. But the good news is that, what is this thing? So I don't think I'm going to derive it in our lecture, because as usual, I'm already going over time. But just to kind of eyeball a little bit, you have a quadratic objective function, right? You see that your unknowns here, Zi and Zj, are appearing twice. And you have one quadratic constraint. So if you write down the KKT, or really just Lagrange multiplier expression for this constrained problem, what you're going to figure out is that all you're really doing is computing the eigenvector of this matrix H with the biggest eigenvalue. And that up to scale is going to give you, I'm sorry, I'm writing crazily. It's going to give you a vector, maybe we'll call it, I don't know, Z, which is Z1, Z2, and so on, for this relaxed problem. So in reality, here's the only issue, but it's a big issue, is that we didn't solve our original problem. We solved a relaxed one which removed a lot of the constraints on Z. Incidentally, because we removed constraints, that max value will get bigger, right? We're going to upper bound our optimal objective value. But the problem is that we're not going to get unit complex numbers necessarily, Zi. So what do we do in practice? If you want to solve this eigenvalue relaxation of this problem, you compute the top eigenvector of H, and then maybe you just take the elements of that eigenvector and divide each one by its norm to get an estimate of the Z's. And it turns out that this actually works quite well in practice. So in other words, here's a really simple strategy for approximating the solution to this maximization problem here, which is that you relax the constraint and solve the resulting eigenvalue problem. And then to get a Z that satisfies these constraints, you just kind of round by essentially taking the elements of Z and projecting them back onto the unit circle. So this is strategy number 1, which is the eigenvalue relaxation strategy for this problem that I've written on the upper left. Again, the way that we get it is by summing this constraint squared over all the I and just convincing ourselves of the eigenvalue problem. So now let's derive the second relaxation, which is a better relaxation. You can actually show that it has strictly more constraints than the eigenvalue one we've written here. And that is the semi-definite program version of our problem. Okay, so let's do version 2 here, which is a semi-definite program, or SDP. Oh, what's going wrong with this marker? It's a brand new one. Okay, so once again, we're going to define 2 objects, one of which also, I guess, appeared in our eigenvalue problem. So we're going to take all of our complex numbers Z and stick them into one long vector. So we'll say that Z without the index is like Z1, Z2, and so on. So it's a vector in Cn whose individual components here are all unit length. And now we're going to make a second definition, which is a matrix. We'll call it big Z. And the way that I'm going to define this matrix is going to be Z bar Z transpose. Now, like in this class, we've seen, V transpose, but here, notice that this first Z is conjugated. And the reason is that that makes this matrix semi-definite in the complex valued case. So if I conjugate it properly with a vector, then this is semi-definite like that. Okay, so it turns out that we can take our problem star, we can write it in kind of a slick way in terms of Z and big Z here. So essentially, we're going to say that the star here is equivalent to maximizing over 2 variables, little z and big Z, the following. Now, this is a sum over all ij, the real part here. And by doing basically the same sort of linear algebra style arguments that we've already made a number of times, we can actually write this as follows. That this is the real part of the trace of H transpose Z. And that's obtained just remember that the trace of a matrix transpose times another is just the inner product of 2 matrices. But here we need to be a little bit careful to account for the fact that there's a real part hanging out here. And we need a bunch of constraints. So for one, well, we need to make sure that the relationship between big Z and little z is actually enforced. So big Z is equal to little z bar little z transpose, like that. And by the way, just for fun, I can actually add a constraint on big Z, which is sort of redundant with the first one, which is that the rank of big Z is equal to 1. And that's actually exactly what that first constraint is saying. Now, what other constraints do I need? Well, I need that the modulus of each zi here is equal to 1. Now, remember that if you think about the diagonal of this matrix big Z, you'll see that that's exactly zi times zi bar, right? That's what this diagonal is. So a fancy way of writing our constraint here is that the diagonal of big Z is equal to all 1s. And finally, we can write, just for fun, our observation here, which is that big Z is semi-definite. Okay? Here, this inequality, I can never write it properly on the board. This is the semi-definite sign. It's not just that it has elements that are greater than or equal to 0. In fact, that wouldn't make sense here because big Z is complex value. So here's the kind of cool thing, which is that this problem here is equivalent to the box problem that we wrote in the corner. Now, why is that? Well, essentially, we haven't done anything. All we did was introduce big Z, write the constraint in terms of big Z and the objective function. Oops, that should be a big Z. My apologies. which is perfectly fine so long as we add a constraint that enforces the relationship between the little z and the big Z. But here's a kind of sneaky trick that we can do, which is that notice that little z now only appears in one constraint, which is this guy. And that constraint is actually redundant with the rank and semi-definite constraints. It turns out that if I can take a complex matrix whose rank is 1 and that is semi-definite, then, well, just by definition, a rank 1 matrix can be written in this form. So one thing that I can do is actually drop this first constraint, and the problems are still equivalent. Okay, so this problem, even though little z actually doesn't appear anymore, this problem is still equivalent to the starred problem here in the sense that I can obtain the solution by doing the following. I solve this problem in big Z, and now I know that big Z has rank 1, so I can compute its eigenvector, and only have one eigenvector because it's rank 1, and that eigenvector necessarily will be the solution to our problem. So this is kind of sneaky because we've eliminated the little z variable altogether. And now we just have a big Z variable. There's only one problem, which is that this is an extremely non-convex optimization problem. And that is due to this constraint right here. This is the hard one to work with. The set of rank 1 matrices is like, it cuts out a weird algebraic variety in the set of all possible matrices Z. And so that's the constraint that's hard to enforce. So what do we do in our relaxation? Well, our relaxation simply removes this constraint. Okay, so what we're going to do is remove this constraint to relax our problem. And what we're left with is a convex optimization problem. And this is kind of cool because notice that our objective function is linear in Z, right? It's just the trace of H transpose times Z. Turns out, by the way, the real part's actually unnecessary here, but that is perfectly fine to leave it there. We're getting rid of the annoying rank constraint. That goes away. And the remaining constraint, one of them is just an equality constraint, right? It's just constraining the diagonal elements of Z. And the other is that Z is semi-definite, and the set of semi-definite matrices is a convex set. So what does that mean? That means that we can solve for the optimal big Z here if we drop that rank constraint. And what do we get? Well, unfortunately for us, we don't necessarily get the solution to our problem. So in practice, what you have to do is you optimize for big Z by calling your convex optimization software like CVX. And then maybe you take the top eigenvector of Z, or actually the more kind of principled thing to do is a particular randomized rounding strategy where you use Z as the covariance of a Gaussian distribution, sample, and then round. I'll let you guys do your own reading on that. But the basic point here is that we've massaged our problem. This thing with the rank 1 constraint is equivalent to our original angular synchronization problem. And just by dropping this one rank constraint, we now have something convex, so we can actually extract the global optimum. And it turns out this is a stronger relaxation than the eigenvalue one. I'll let you convince yourself that at home, that essentially by removing constraints from this problem, you can recover the eigenvalue problem that we wrote down before. I'll give you a hint. The way to do that is to replace this diagonal constraint with a constraint on the trace of Z. Okay, so right, so this is a kind of an interesting strategy. And one of the kind of cool empirical things you might notice if you try this at home, and I strongly recommend that you do, is that oftentimes you'll solve this optimization problem without the rank 1 constraint. So like, you know, you get rid of this box thing and you solve with just these 2 constraints. And the solution that you get ends up being convex, or rather rank 1 anyway. What does that mean? So I dropped the rank 1 constraint, I optimized, and I got the global optimum of the relaxed problem because it's convex, and it happened to be rank 1. Well, if I'd added that rank 1 constraint back, I actually my optimal solution wouldn't change because it was already rank 1, right? So, in other words, if the solution to the relaxed problem just happens to satisfy rank z equals 1, so somehow we got lucky, well, then we know that z is the global optimum of the original problem. Oops, I apologize for horrible handwriting. The original problem. So this, I think, is sort of a non-controversial sentence. The only question is like whether it's useful mathematically. And the answer empirically is actually yes, that oftentimes when we solve this convex problem where we've dropped the rank constraint, we get a rank 1 solution. And this is this surprising and beautiful observation about these sort of SDP relaxations of these rank 1 style problems. Now, here's the basic point. Oftentimes, when I solve an optimization problem that's non-convex, I have some crazy constraint set. You know, like there's no reason why my constraint set should cut out a shape which looks convex. But essentially, we did all of this work here to massage our problem into a form where our objective function is linear. So we have a linear objective function, and if we leave that rank constraint here, then we have some crazy set of constraints that cuts out a weird, feasible set for our problem. However, we know that our objective function is just a giant arrow. Why do we know that? Well, it's just a linear function in z. So here is kind of a simple observation, which is that actually, anytime you have an optimization problem whose objective function is linear, it doesn't actually matter what the constraint set is. You can show that the optimal point for your non-convex constrained but linear objective problem, so it's always going to end up on the convex hull of the constraints. You can kind of see that here, right? Because the objective function here is just saying move me as far to the right as I can, right? So my optimal point is here. And notice that if I were actually working on the convex hull of my problem, that optimal point actually wouldn't change. And this is the kind of beautiful thing that turns out to be kind of going on behind this SDP relaxation, which is that we removed constraints, but somehow we removed just enough of them to make our problem convex. Now, where can this go wrong? It can go wrong in two ways. So one of them is that we didn't actually compute the convex hull. So the convex hull is the sort of smallest set of constraints that is convex and contains the constraint set for our problem. And I didn't actually argue that dropping this rank constraint gave me the convex hull of our original constraints. It is true that the convex hull of rank 1 matrices is semi-definite matrices, so it's somehow linked, but we've added some more constraints, so that's no longer true. Or it could be that there's some symmetry in our problem. This one's also a bit annoying. So like think now if I had a constraint set that looked like this kind of a shape, and my objective said go to the right, well, if I convexify it by computing the convex hull, I could accidentally get a point here. And the reason is that there's two optimal points that are equally good, but there's something in between them that's not so great. So in any event, the really non-trivial mathematical work that you would have to do to show that this strategy is successful is to make sure that there's no symmetry in this problem that you don't want, and to make sure that your constraints are actually the convex hull of the constraints. But empirically, it turns out that this relaxation strategy works really well and often gives you the global optimum for this angular synchronization problem. So anyway, hopefully I've given you some idea of how to derive a pretty reasonable, nice technique for angular synchronization that is actually really pretty easy to implement. You just code up, you extract this matrix H, and then you solve this convex problem, and there's plenty of software out there that can solve semi-definite programs to spec. Okay, so hopefully now you get some idea of the flavor of methods we can use for convex relaxations of synchronization problems or consistent mapping problems. In lecture, we covered one that involves synchronization of permutation matrices, and that led us to one semi-definite programming formulation. Here we just covered another one for synchronization of angles, which is somehow actually kind of a simpler problem to solve, but one that's a little less directly connected to our consistent mapping problem in geometry. Now, there's many interesting extensions that I thought are worth a mention here. In particular, we can synchronize data that kind of comes from any group structure, and really I do mean group in the algebraic sense. I think one of the kind of reasonable ones, here we only synchronized angles, so the best we could do for like registering a bunch of bunny scans for with each other would be like if they were sitting on a turntable that was rotating. But of course, a reasonable extension might be to SO3, which is rotations in 3D. And there's many different ways to do this, and I can give you guys some pointers on Piazza or on the course discussion board if that's useful. Sort of the simplest thing to do might be to replace complex numbers with 3x3 matrices. So in this case, what you'll end up with when you do your semi-definite matrix relaxation is now this matrix Z that we had before is going to have like 3x3 blocks in it, where the diagonal 3x3 blocks are the identity. Right, so the different blocks in Z are kind of like the relative motion from one rotation to another. One issue here is it's going to be hard to get rid of certain types of inversion. So other folks use a different representation, which is the quaternions. And you can come up with a quaternionic relaxation by basically just following the same path that we have derived in class today, which is pretty nice for synchronizing rotations in 3D. Turns out higher than 3D, now your life gets a lot harder. Now, the real holy grail here is maybe not to work with SO3, like rotations in 3D, but actually to work with SE3. And this, of course, is rotation and translation. And it turns out that coming up with convex relaxations of synchronization in SE3, this is a hard problem. By the way, I guess I mean hard in the psychological sense and also in the NP hard sense. So in particular, the reason why this is hard somehow philosophically, if you're familiar, is that SE3 is a group, but it is a non-compact group. What does that mean? Well, SE3 includes translations, and there's no bound on translation typically. And so what that means is you have variables that can go off to infinity, whereas in synchronization in SO3 or angular synchronization, our angles our complex numbers had length at most 1. And that turns out to make the convex relaxation somehow much easier to work with. So there have been various attempts to take the sort of strategies that we've covered here and make them work. Maybe you just write it as a non-convex problem, try and solve it, and it works well in practice. In fact, I think that's the typical strategy. So in computer vision, you might call this like bundle adjustment, or a different word for it is structure from motion. These are not quite the same, but they're closely related. And basically, they look like synchronization problems, but now the things they're trying to synchronize are like I take a bunch of photographs of a scene and I get an estimate of the rotation and translation, or maybe even the camera motion from one photograph to another, and now my task is to put all of the photos into a common frame and maybe reconstruct the scene while I'm at it. I think that the sort of typical strategies for these kinds of problems worry a little bit less about getting the global optimum and instead just worry about getting something useful. So if you're willing to work with a non-convex problem, like maybe the problem we started with before we did all our relaxations and just doing gradient descent, that's perfectly fine. And I think many of the strategies for these kinds of problems kind of live in that space. Another kind of interesting approach, which is due to Nir Sharon and colleagues, is maybe to compactify it. This is kind of an interesting idea. So if you read about the stereographic projection of this, like Rn onto a sphere, essentially you can often take things like the real line and almost stick them onto a compact space. So for example, let's say that I had a one-dimensional but infinite set of variables. I could like stick a circle sitting right here, and then I can actually map the one-dimensional line to the circle through this map where it takes a point, follows the tangent, and then this is sort of a correspondence. So for every point, I follow the tangent to the circle down, and I get a point on the real line. And as I move to the top of the circle, notice I go farther and farther out. This is called a compactification of the real line, or the stereographic projection. And it's one way to kind of take the translation part of SE3 and maybe put it onto a spherical space, which we know how to cope with in convex relaxation. But the problem is going to be that like different translations are treated differently. Like this little space on the unit circle is like dealing with 99.9% of the real line down here. So somehow it's quite hard to come up with a reasonable objective function in this setting. But these are essentially new, open, challenging problems, synchronization and non-compact groups, and I think we'll continue to see some interesting research in that space. But again, if you're less worried about convexity and global optima and more just getting something, there are plenty of bundle adjustment and structure for motion algorithms out there that just tackle a non-convex problem and do perfectly well, even if they don't have guarantees. Incidentally, one last thing before we close. Another fun application that's quite similar to all of these and popular in the microscopy world is something called Cryo Electron Microscopy, where here I'm trying to image a macromolecule. And what ends up happening is I have my electron microscope, which I approximate with a cylinder. And there's a beam that goes through the microscope and onto a sample of my molecule, which is like down here. And then I have a sensor sitting underneath. So what I get back is like a projection of my molecule onto the plane of my camera. And if I do that with a big sample of this molecule, then I get it in all kinds of different conformations, like rotating around. Then the cryo-EM problem tries to take all of these projections of some macromolecule I'm trying to image onto a plane and extract one 3D structure. And hiding inside of that is a problem that looks very similar to synchronization, but now you have even less information because instead of having relative motion, you just have the projection of your molecule onto the camera plane. So there's some really interesting strategies that try to take ideas from the synchronization world and make them work in this partial case. One of the kind of fun ones from the same author of the paper that we covered today uses common lines, which I think is sort of a clever trick. And I think there's more strategies coming out year by year. You know, the cryo-EM I think got a Nobel Prize not so long ago, so there's a lot of excitement algorithmically on taking some of these synchronization methods and making them work for these big data sets of extremely noisy proteins projected onto camera planes. So in any event, hopefully you have some idea of the flavor of techniques we use to derive convex optimization problems to solve synchronization. And there's much, much, much more. I mean, you could construct an entire course around this sort of thing. But at least we have some heuristic idea of where the high-level ideas come from. The other important thing to mention is just that many of these algorithms also come with statistical guarantees. So for example, the angular synchronization with semi-definite programming technique we covered today actually has some guarantee that you'll get near the global optimum, even with that relaxed problem, if those delta ij's are basically known up to Gaussian noise. So anyway, with that, we will see you next time and hopefully enjoyed this little digression into an interesting area in applied math and computation.